All right, so today we're going to talk about enthalpy, and so you should have a notes page. This video is mainly for those of you that are absent, so that whenever you get back to class, you can get caught up on the notes that you missed. Or if you're at home, you are more than welcome to watch this video and then do the assignment. This stuff is pretty straightforward, but like I said, there is a note sheet, but the notes, however, are not graded. It is the assignment afterwards. So we're doing these notes on Monday, April 25th. So what exactly is enthalpy? Well, enthalpy is the measurement of the heat that has been absorbed, which based off of the doodle notes that y'all did on Friday, that means that it is endothermic because it's absorbed, which means it's going inside, and we're talking about heat. So inside is endo, heat is therm. So the measurement of the heat absorbed, which is an endothermic reaction, or released, which is an exothermic reaction. So released means you're letting it go. It's going outside. So that's exo. And then once again, therm is heat. So outside heat. So measurement of the heat absorbed, which is endothermic, or release, which is exothermic, by a chemical reaction. This can also be calculated with this following equation, where H, and that should have a delta there, delta H is equal to the products minus the reactants. And we just call delta H is known as enthalpy, change in enthalpy. So the H of the products is the potential energy content of the products, also known as the enthalpy of the products or total enthalpy of the products. So H is enthalpy, and then H reactants is once again the potential energy content of the reactants or the total enthalpy of the reactants. They're used both ways. Really kind of just depends on if you're looking at the graph or if you're reading a problem. If you're looking at a graph, you kind of talk about the potential energy. But if you're reading in a problem, they'll probably say the total enthalpy of a product or total enthalpy of a reactant. So when we calculate this, we're going to get a value, and based on what this value is, based on whether it is a positive number or a negative number, that can tell us what type of reaction we have. But first, let's go ahead and discuss endothermic and exothermic again. So how is heat flowing in these two pictures? So looking at the picture on the left where we have a human's hand, someone's hand is holding an ice cube. And of course, so you got the ice cube in your hand, so what's the ice cube going to do? Well, the ice cube, of course, is going to melt, as you can clearly see here. So with the ice cube melting here, all right, how exactly is the heat flowing? How's the heat flowing? Is the heat flowing from the ice cube to the hand or from the hand to the ice cube? Okay, so that's one of the questions that we're answering. So looking at this one here, we have which one is naturally warmer, and of course the hand is naturally warmer. So heat, my bad. So heat is actually flowing from the hand to the ice cube, and remember it's the ice cube that we're paying attention to. So because the heat is flowing from our hand into the ice cube, that means the ice cube is absorbing energy. So it's taking in that heat from our hand, and so therefore that is an endothermic reaction because it has to absorb the energy in order to melt. Now, when it absorbs that energy from our hand, so when it takes heat from our hand, so our hand is losing heat, our hand is going to feel cold. Now, if we do the opposite one, so this one is melting. If we go over here and we talk about freezing and making ice. So to do ice cubes, you have to start out with liquid water, and then it goes into an ice tray, and it goes into your freezer. Well, when it gets into your freezer initially, it is liquid water. Okay, so we have liquid water, and then it's going to freeze. So we're going from liquid water to freezing. So think about how is heat going to flow here. So if we want the water to freeze, remember, because we're putting it inside of a freezer. So this ice cube tray starts out with liquid water. If that water needs to freeze in order to make ice cubes, is it going to gain heat or is it going to release heat? Okay. And the actuality is that the liquid water is going to release its heat into the freezer because we are going from liquid to solid. So we need to let off heat because what is colder, liquid water or ice cubes? And ice cubes are colder. So in order to go, if we're already hot, in order to get colder, we have to get rid of that heat. So Freezing is going to release heat from the liquid water into the freezer. So whenever it releases that heat, when that water releases that heat, then it goes from liquid to ice. So we're going from liquid to solid. That is an exothermic reaction because it is releasing the heat. So the big thing is, so endothermic is taking in heat. Because remember, what we're paying attention to is we're paying attention to the ice. Here, the ice cube is melting, so it's taking in heat. So that's endothermic. Here, we're still paying attention to the ice, but it's initially starting as liquid water and then turning into ice cubes. So the heat is flowing out of the liquid water into the freezer in order to make ice cubes. So that is exothermic, it's flowing out of. So how does this look on a graph? Well, our first graph we're going to look at is we're going to look at endothermic. So remember that endothermic is inside. Okay, so we have inside. So right here is our graph. So our graph shows potential energy and then the reaction progress. So one thing you are going to have to be able to do on the test is you will need to be able to label the graph. The good news is the graph stays labeled the same no matter whether you're looking at an endothermic reaction or an exothermic reaction. Right here, like the way reactions go, remember RAP, reactions, arrow, products. We always start with the reactants and then we end up with the products. So this first part here is always the reactants, and this is potential energy. So if this space right here represents the potential energy of the reactants. Over here is where we end up. So these are our products. So this space over here represents the potential energy of our products. Now, we also want to be able to find enthalpy, or the heat of reaction. So remember that the formula for enthalpy is products minus reactants. So here's our reactants, here's our products. So right here is our enthalpy. Okay, that's our heat of reaction. Now, whenever the reaction first starts taking place, you notice that there's this little hump that's got to go over. So because this one is an endothermic reaction, it has to take in lots of energy in order for the reaction to occur. So this right here, this point here called the potential energy of the activated complex. So this right here is the activated complex right here. It has to get to that activated complex in order for the reaction to occur. So the more energy it takes, the greater your activation energy. So this line right here is your activation energy. And then potential energy, the activated complex, because activated complex is up here, potential energy is always measured from the very bottom. Okay. Activation energy is only from the reactants to the top of the hill. Potential energy, the activated complex, is from the top of the hill to the very bottom of the graph. So here we got delta H of products minus delta H of reactants. So here's our products, here's our reactants. So if we just imagine some numbers over here, so reaction progress, that's just basically time and our potential energy. This is 0, and let's say this is 5, right? So, okay, or let's say this is 1 and this is 5. So 1 is our reactants, 5 is our products. Well, which one's the bigger number? Well, 5 is the bigger number. So in this case here, we're going to have greater energy in our products are going to have a greater energy than the reactants. So therefore the products is going to be a bigger number because see, it's higher up. So these are lower numbers. So, you always start with 0, then 1, 2, 3, 4, 5. So products is up higher, so it's going to have a bigger number, and your reactants is going to be smaller. So when you do big number minus small number, you get a positive number. So 5 minus 3, and these are just arbitrary. So 5 would be the products, minus 3 would get us 2, and that is a positive number. So if you calculate delta H and delta H is positive, that is going to be an endothermic reaction because it had to take in heat, which means because it's having to take in that energy, those products are going to have greater energy at the end. I accidentally left the title the same, so please disregard this, but this should be exothermic. If endothermic was inside, then exothermic should be outside. So here we see an exothermic reaction. Once again, the reaction diagram is labeled exactly the same. You always start with your reactants, and then the reaction occurs and you get your products. Okay, so once again, we're talking about potential energy. Potential energy is always measured from the bottom of your graph all the way up to where you are. So potential energy of the products is all of this area right here. Sorry, this is reactants. Potential energy of the products is all of this area. Remember that delta H is products minus reactants. So here's our reactants, here's our products. So this little area right here represents delta H. Remember that in order for the reaction to occur, you must hit the activated complex. So up here represents the potential energy of the activated complex. This is the activated complex. So if there was an arrow drawn from the very bottom all the way up to the very top, like there is on your paper, then that is the potential energy of the activated complex. The activation energy is the actual energy that is required in order for the reaction to occur. That is only the energy from the reactants to the top of that hill. So activation energy is only from reactants to the top of the hill, whereas activated complex is from top of the hill to the very bottom. So here, if we look here and we compare reactants to products, well, this time products have less energy than our reactants because products are down here. Remember, graphs start at 0, 1, 2, 3, 4, 5. So our products have less energy than our reactants this time. So because of this, like the last one was 5 minus 3 because products was greater than reactants. So 5 minus 3 got us to 2, which was a positive number. But now it's going to be reversed because the products is smaller. So now the products is 3 and the reactants is 5. So 3 minus 5 is negative 2. So when it's a small number minus a big number, which means your products have less energy than your reactants, you're going to get a negative number. So when you calculate delta H, if your delta H is negative, that's how you know it is an exothermic reaction. Once again, this should say exo and that should say outside because exo means heat is leaving. You're giving off heat. Notice how all the energy we started with, all that energy is gone. That energy was given off in this reaction. So that's why the products don't have as much energy. So here's your example. So example number 1 says that the total enthalpy of the products is negative 685 kilojoules and the total enthalpy of the reactants is negative 682 kilojoules. What is delta H? And then it's also asking you, is it exo or is it endothermic? All right. So first we need to calculate delta H. Well, how do we do that? Well, delta H is the products minus the reactants. So we read our problem again. Right here it says our products is negative 685 kilojoules. And right here it says our reactants is negative 682 kilojoules. So now we're going to put in our numbers. So delta H is equal to negative 685 minus negative 682. So what do you do when you minus a minus? Right? You're going to add them together. So you can say the same thing as negative 685 plus 682, or just leave it like this because this is what the equation is. So negative 685 minus a negative 682. So when we calculate that, we get negative 3. So our answer is negative 3 kilojoules. Now it's asking, is it exothermic or endothermic? Well, look at your number. Do we have a positive number or do we have a negative number? In this case, we have a negative number. So that is going to be exo, okay, because it's negative. If this was a positive number, that one would be endo, okay. Example number 2. So you're also going to be given graphs and have to identify what type of reaction it is. So this one, here's a graph, and we want to know what type of reaction is it. We're talking about whether it's endothermic or exothermic. So here's our graph, here's our reactants, here's our products. So if we're looking, our products have less energy than our reactants. Okay, so you can look at it that way. So which one has less energy than the reactants, which that means, okay, so we have all this energy, and then when we're done, that energy is gone. Okay, that means the energy was given off, so the energy was lost. Okay, so you should already kind of think of which one that one is. Or you can assign arbitrary numbers. Whichever one is higher up has a bigger number, whichever one is lower down has a smaller number. So I'll just say this is 1 and this is 2. 1 minus 2 is negative 1. So I would get a negative delta H in this case. So that is going to be, comparing our reactants and products, my bad. So that is going to be exothermic. And that is because the product has less energy than the reactants. So when you're looking at your graph, remember this is the graph of your reaction. When the reaction starts, we have all of this energy. But then when the reaction finishes, we don't have that energy anymore. The energy was lost. So when you lose energy, that is an exothermic reaction. All right, so now your next assignment is to go to Schoology and complete the Enthalpy Practice 425. It is going to be a total of 10 questions. It is unlimited submissions, so if you don't like your grade the first time, feel free to do it again as many times as you want to make a 100.